On this lecture video, I'll be discussing the ion-dipole interaction, which is the last types of IMF that we'll be discussing here in this class. And then we will do a quick summary to compare all of the IMFs that we have discussed already. So now let's discuss the ion-dipole interaction first. This types of IMF right here is the strongest of all. The strongest types of IMF. It is even stronger than the hydrogen bond. But now, here's the catch. These types of IMF right here do not exist in a pure substance. If we were to have a pure substance, then we will never see the ion-dipole interaction. Okay? Because we will only be able to find this ion-dipole interaction right here in a solution. And we know that a solution is not a pure sample, right? So this exists in a solution of an ionic compound and a polar solvent. So whenever we take an ionic compound and dissolve that in a polar solvent, such as water, then this is where we will find these types of ion-dipole interaction right here. And again, although this is strong types of IMF, even stronger than the H bond, but they do not exist in a pure substance. So for a pure substance, the strongest types of IMF they can make would then be H bonding. Okay? But again, this is stronger, however, only exists in a solution. And so when we take an ionic compound and we dissolve that in a polar solvent, then we have seen already that if the ionic compound is soluble in the polar solvent, it will be broken into individual ions as it gets dissolved, right? And as the ionic compound is broken into ionic compound, which are broken into the ions, which consist of the cations and the anion. The ions, whether cations or anion, are now interacting with the polar solvent, and that's what makes up the ion-dipole interaction. So because the solvent is polar, it will then have a dipole to it. And now an ionic compound have ion in it. And now the ions, whether cations or anion, are now interacting with the dipole moment from the polar solvent. And therefore, it's named ion-dipole interaction. And so this is the types of IMF right here that actually determine the solubility of an ionic compound in water. If the ionic compound are able to make very strong ion-dipole interaction with water, then that is when the ionic compound tend to be soluble in water. Okay, so the stronger the ion-dipole IMF, the more soluble the ionic compound in water will be. And now let's see how this ion right here are interacting with water or another polar solvent. But let's use water as an example. So in water, when we draw the structure of water, we see the following. There is two dipole moment in water, right? And that is both now pointing to the oxygen. That makes this oxygen here partially negative and the two hydrogen partially positive. So that's how the partial positive and partial negative charge work out in water. So let's see how this would then interact with the ions. So let's say that we take sodium chloride and we dissolve that in water. Then this is the interaction that we will find right here. So in the case of the chloride is negative. Because this is negative, this E now will be interacting with the hydrogen, right? Because it is the hydrogen from water that carry the partial positive charge. So basically, water will reorientate itself to basically put in the hydrogen facing toward the chloride. So that way, they can interact through this ion-dipole attraction right here. And this is a strong type of IMF. Why? Because it actually involves something that is fully negative. Anytime we have something that is fully negative or fully positive, they will be strongly attractive to something else that is partially positive or partially negative. So this is strong, and this is the ion-dipole attraction right here. And as you can see, many water molecules will be surrounding this chloride right here, where all of this water molecule would have the hydrogen pointing to the chloride. And we will find many of this ion-dipole attraction in this case. Now, what happened to the cation then? So as the cation is dissolved in water, it will be surrounded or surveyed by the water molecule, in which that the water molecule would now reorientate itself, in which that the oxygen is now facing this sodium ion right here. And again, because the sodium is positive, so therefore water will then put out its negative end, so that way it can interact with the sodium cations. And this again is a ion dipole attraction right here. So you can see there's many of this ion dipole attraction between the ion and the water molecule. And that dictates the solubility of the ionic compound in water. And now let's do a quick comparison of the different types of IMF. So first we have seen the dispersion force already. And this is present in all molecule and atom. And this is a function of size. The bigger the molecule, then the stronger the dispersion force will be. And this consists of the temporary dipole moment, as what we have seen right here. And the next one will be the dipole-dipole force. And this exists in all polar molecule, where now we will actually have the permanent dipole moment that are interacting with each other. And next would then be the hydrogen bonding. So the hydrogen bonding basically exists in molecule containing hydrogen bonded to fluorine, oxygen, and nitrogen. And to be more clear, it is the interaction between the H bond donor and the H bond acceptor. So all of this can exist in pure substance. And lastly, the ion dipole. So this exists in a mixture. So this will be an impure sample right here, a mixture of an ionic compound in a polar solvent. That way we'll find the ion dipole interaction. And in terms of strength, then this is how they are ranked right here. The dispersion force is the weakest, followed by the dipole-dipole and the H bonding and the ion dipole.